This is a production of Cornell University.
Any questions? Hope everybody had a great weekend, prepared for the windstorm that's about to descend on us. That's just not my lecture. It's, the next couple days. Any questions? We're pretty good. We feel comfortable with nitrogen and sulfur. Today we're going to be talking about phosphorus and potassium. And they're going to be the last two nutrients that we're going to be talking about. And I'm continuing to progress from the most extreme biologically mitigated, extreme, that's probably not the right word, the most, I don't know, we're venting already. In essence, I'm going to say most extreme, but the most extreme of the biologically mitigated processes, nutrient cycling to potassium, which when we start talking about it, there's actually no microbial mediation whatsoever. There's literally no biological mitigation whatsoever. So let's start with phosphorus here. Okay, phosphorus is another macronutrient. It's basically essential for ATP, RNA, and DNA, so for our replication as well as for energy. It's an essential element of cell membranes. This is the hydrophobic issue. Yet still only 0.02 to 0.04 of leaves and approximately 2% of dry matter have this in it. So while it is a macronutrient and it's essential for a lot of different things, there's actually not that much of it that's in our biomass. You've seen slides like this before, but let's talk about where that phosphorus is. Ocean and ocean sediments seem to be the really dominant here. Basically, it's stuff that's sitting at the bottom of the ocean. There's some that's in the water column dissolved, and then in organic and detritus biota that's actually sitting in the ocean or swimming in the ocean. From a land perspective, there's the dominant pool of it is the soil itself. It's in the soil. Okay. There's also a sizable portion of mineral rock. This is basically where we get phosphorus for fertilizer, and I'll talk about that in a little bit later. There's the pool of us as well, the biota, and then there's in the fresh water in the terrestrial system. I should say terrestrial system, but in the upland systems, not oceanic. So there is a pool of it in the fresh water. If you think about this from a soil's perspective and a plant's perspective and our perspective, this pool right up here is what we're managing for. Okay, so what do these pools look like, and what are the fluxes between them? Atmospheric has a very small component. We're really looking at this really large pool that's sitting in the sediments of the ocean right here, and you're basically looking at the dissolved, the biota, and the detrital material basically ultimately ending up here. There's not a lot of feedback from here this way. Yes, there's some going up into the atmosphere, and yes, we dredge materials all the time, but there's just not enough of this moving this way to recharge the phosphorus pools up here. Okay, most of the pools that we see here, actually let me take a step back. In a time scale that's biological. In a geologic sense, all of this stuff is going to be going back into rocks. Okay, and literally it will come right back up here. But that's a geological time scale versus a biological time scale. Okay, so for where we're looking at, we're basically looking at the phosphorus that's in this pool right here, which is in the soil. Yes, there's some coming from mineable rocks, and we're using this basically as our fertilizer. We're digging this up and applying it as fertilizer. This pool is in the biota through humans, and then ultimately it gets into the fresh water or through erosion and ends up into the ocean. Okay? Seems pretty straightforward. Yeah, questions about it? Okay, what we're going to be talking about is really sort of these fluxes, and we're going to be mostly focusing on this component of this cycle. Okay, so those sources and the sinks. The sources, the parent materials are primarily apatite minerals, but there's some other parent materials. The phosphorus ranges are from 0.01 to 0.2%. Okay, so fairly low concentrations. Now, remember when I talked about those leaves, in a sense, yeah, this is low concentrations, but we don't actually need a lot of it for our biomass. Okay? The native soil concentrations, on the other hand, are 200 to 2,000 micrograms. per gram, significantly larger than what's in the mineral rock. Okay, we also have it coming in as fertilizer and manures. Basically, 10 to 15% of the fertilizers of this phosphorus is coming in as fertilizer is taken up by plants. Okay, so of that efficiency, if we're adding fertilizer onto the system, basically 10 to 15% of what we're adding actually makes it to the plants. Okay, so where does that rest of that stuff go? If we look at the soil pool itself, here I put this slide out here again so you guys can see this number, these numbers. The soil, the amount of phosphorus that's available for biological activity is actually rather small. Yes, the soil pool is rather large, but of that pool, a very small amount is actually available for plants, and we'll talk for organisms in general, plants in specific, and we'll talk about that in a moment. The bulk is in basically 3 pools, and those pools are an organic phosphorus bound pool, a calcium-bound inorganic pool that tends to be at the higher pHs, and an iron and aluminum-bound inorganic phosphorus, which tends to be at the lower pHs. This scale that you see here, or this graph that you see here, this is the extent of phosphorus retention in the soil, okay? And this is the pHs, okay? So we're looking at low pHs here, high pHs here, so alkaline soil versus acidic soils. Okay, you'll look at this pool right here, this bar graph right here. This basically means the sorption of phosphorus with iron and aluminum. Okay, so that is this pool right here. Okay, as the pHs rise, we start seeing the binding with the calcium. Okay, so we have calcium phosphate bound phosphorus. Now it turns out that both of these pools are basically insoluble, which means in essence they're unavailable for biological uptake. Okay, they're not going to go into soil solution all that easily. It does, but it's basically sitting in the soil in an insoluble form. Okay, now there is another pool, and that's this organic phosphorus pool, and that's actually throughout this. I mean, there's organic molecules throughout. It doesn't matter what the pH range is, but that phosphorus is also pretty much unavailable for plants, for organisms. Now, to take a look at that a little bit better, this is that distribution. I've blown this, the last slide, this is from your book, but that last slide I've basically blown it up into a different slide. I've taken this slide from the book, and what you're looking at here is on this axis, you're looking at the distribution of phosphorus. Okay, here's the soil pH, okay, and here is the distribution of phosphorus at the lower pHs in those iron and aluminum oxides. Okay, there's basically these, and they're insoluble and they're unavailable. Okay, at the high pHs, we're looking at that calcium pool. Okay, and if you look at this, there's a very relatively small range of phosphorus that's available, and it's centered around that pH of 6.5. Okay, small pool. So going back to this slide right up here, the soil, there's a good chunk of phosphorus in the soil. But just because it's in the soil doesn't necessarily mean it's available for the plants. And that's where we see this slide. Okay? Of that 100%, if you're down at the pHs of 4, a very, very small portion of that is available. Most of it is bound and unavailable. All right, so let's take a look at the soil surfaces across the United States. Phosphorus in the soil, not only do we have this issue that most of it's bound, okay, but we also have a potential issue of where it is in that distribution. So we look at sort of the coastal plains in the southeast and then moving up into the northeast, you're looking at fairly low levels of phosphorus that are in the soil. Okay. As you move west, because of the primary minerals, apatites primarily, and the younger rocks that we have out west, we tend to see much more of the phosphorus in those soils. Now, having said that, there are 2 primary mineable areas of the United States where we get phosphorus. One of them happens to be in Florida. We're basically mining rock phosphate. Now, this is, in essence, this is a non-renewable resource, and you saw how little of that pool, if we look at the mineable rock versus the soil, there's a very small pool of phosphorus that are in those rocks compared to all the other phosphorus pools. Okay? Now, looking at the soil component of it, remember I want to talk just about the soil component. Okay, here's the soil solution. Okay, organisms basically and organically bound phosphorus. Here's two different pools of the calcium-bound phosphorus. This is the calcium-bound phosphorus, and this is the iron aluminum-bound phosphorus. Okay, plant material, fertilizer, and the biomass. Okay, so let's go through this. Okay, and we're going to start with the soil solution. Okay, now from the soil solution, the phosphorus can get into the plants. Okay. Yeah. I don't think I showed a slide yet. Yeah, I need to make a point, and I forgot that I should have said this earlier. When we talk about phosphorus uptake by plants, it's important to note that plants can only take, primarily plants can take it up as an inorganic form. The organic form is basically unavailable. Okay, so for plants to be able to access phosphorus, it primarily has to be in an inorganic form. And that's what I'm showing on this slide, and I'll talk about this slide later. But what I want you to see here with this slide is these are those inorganic forms that the plants can take up. Okay, now depending upon what the pH is, that form is going to be changing. Okay, now keep that in mind when I go back, and I'll come back to this slide in a second. Okay, but keep that in mind that the phosphorus has to be in a specific form for the plants to take it up when we look at this graphic. Okay, so that inorganic phosphorus, and that's why I took the slide, I shifted here. I didn't realize the slide had not said that. But that inorganic phosphorus in that soil solution is available for the plants. Okay, now the inorganic phosphorus is also available for the soil or other soil organisms. Okay, microbial populations. Okay, they are immobilizing it. The plants are taking it up and essentially immobilizing it as well. All right? Okay, now this biomass and this biomass, both of these biomasses can die. We can harvest it. We can do whatever. We can uptake it into higher trophic levels. Okay, but sooner or later, those organisms are going to die. Okay, which means that phosphorus is now, or because it's been immobilized, that phosphorus is now in organic form, okay? And it comes down as a residue. This material can be decomposed, and in the decomposition of this material, it can be mineralized back into the soil solution. Does that make sense? Now, it turns out a lot of this phosphorus in this organic material is also unavailable because it doesn't decompose, or it has slower rates of decomposition, okay? And so I have a large pool that is basically bound, of phosphorus that's basically bound with organic material that is not available for plant uptake. Remember, it has to be in that inorganic phase to be taken up. Now, once it gets in the soil solution, yes, it can be taken up, but other things can happen to it. And this depends primarily upon the pH. If it is a high pH, okay, this phosphate can bind with calcium, okay? And if it binds in these calcium, it's pretty much unavailable. Now, having said that, it is possible through cation exchange capacity and through decomposition processes for this stuff to actually go back into the solution. But if you look at the size of these arrows, most of this material is going into the calcium-bound pool and basically becoming unavailable. Does that make sense? Now at low pH, it's the same thing will happen, but it will be bound with aluminum and iron. Some of this can be desorbed and put back into the solution, but most of it is going into these pools down here and basically being unavailable to the plants. Okay, questions? Go.
Is it ever the case where there's not enough calcium in the soil
So the question was, is it ever the case where there's not enough calcium in the soil for the phosphorus to bind to? And the answer is yes. Okay? And the answer is yes for two reasons. One is it can be because of a pH issue, where the pH is just low enough, there's not enough calcium. But another issue is where we could be loading so much phosphorus into the system that the calcium, while there is plenty of calcium there, there's not enough calcium to take the load that we're forcing on the system. And that we often see a lot of that around here when we start looking at cow and manure operations. And we'll talk about that in a bit. Okay? Now, having said that, one of the primary sources of us getting phosphorus in the soil, if our phosphorus is in either of these two pools or this pool, it's in the soil, we've got plenty of phosphorus there, but it's unavailable to the plants. So we need to have a way of getting that available to the plants. Conventional agriculture basically says, well, we're going to add some more of this phosphorus. And the reality is that some of this is desorbing. So there is some phosphorus going that way. And what I can do is if I add enough of this, yes, I'm going to be driving the system this way, but I'm going to have some going that way. And if I have some going that way, it means my plants can take it up. Okay, does that make sense? Lily?
When you get a soil test back, what type of phosphorus is it measuring?
When you get a test back, they're also going to be doing pH. And so they're going to figure out what the phosphorus is that's available for your plant. They're not going to be doing total phosphorus numbers. Okay? Does that make sense? All right. Any other questions? Do we feel comfortable with this? Yeah? Okay. Okay. So once again, this question, if we're talking about this, we're talking about trying to see what's going on in here, we need to have a fairly good understanding of what's controlling these fluxes, because that's what's controlling putting this phosphorus in the soil solution. If we're thinking about this from soil fertility for plants, we need to have an understanding about what is forcing mineralization or desorption here. Okay? This is not mineralization. This is already in a mineral form. Okay? It's just because it's bound to calcium or aluminum iron, it's in a mineral form that's not available for the plants. So we have to have an understanding what's going on with those fluxes. All right. So you've seen this slide before. The question is, what's controlling these fluxes and these reactions? Okay? And this is where we get to this slide. Okay? Now, again, biological uptake is primarily in this inorganic form, though some organic P can be taken up. Okay? Phosphorus in the soil solutions range from these very small numbers down here. Okay? So what is it that's driving this reaction? Okay? And it has a lot to do with how the phosphate, what's the ionic form of that phosphate. At high pHs, 10s, 12s, we're looking at HPO4 minus 2. Minus 2 sound, okay? If we start raising it up more calcium is binding in the system, PO3, minus 3. As we move down, we're looking at H2PO4, or PO4, and then ultimately we're back, when we're really low, we're basically looking at phosphoric acid. Okay, these are the forms of those ions that are in solution. These are the forms that are reacting with the calcium, the iron, and the aluminum. Turns out that right around here, at this point right in here, the phosphorus is most available for the plants because it's the least available for binding with calcium and aluminum and iron. Does that make sense? So it's really, generally we think, well, it's the most available. The reality is it's the most available because it's the least available to react with calcium and aluminum and iron. Okay? Good? All right. Which brings us right back to this. Okay? Now, let me stop here. Do we feel comfortable with this?
This has been a production of Cornell University, on the web at cornell.edu.